Okay, our next scheduled talk is Bob Anderson, who's going to talk, I understand, about a new testing system for characterizing video cams. And we just heard about such a testing system with the EXTA, and we'll see how this one compares to it. So whenever Bob's ready.
We'll release. I'll ask Bob to go ahead. Good afternoon from Portland, Oregon. Do we have audio? I'm Bob Anderson, the programmer behind ArtStar and Ocular. This presentation is about two test systems that I put together for characterizing video cameras, like the Wattec 910, together with the frame grabbers commonly used to capture videos from these cameras. My motivation for building these systems was to determine, by direct measurement, whether the mathematics employed by ArtStar is consistent with the actual behavior of typical cameras used for occultation observations. That goal was quickly achieved. Then the project took on a life of its own and has evolved into a second simplified system that I call ArtStar Lite. Next slide, please. Both ArtStar and ArtStar Lite are test systems to be used from the comfort of a desk chair with normal lighting. They were designed for testing video cameras like the Watt 120N Plus and the Wattec 910, plus the frame grabber that's used to record the video. And I really want to stress that in these systems, what is being tested is a camera and frame grabber combination. So when some unusual phenomena is observed, the first question to be answered is, did the camera do this or did the frame grabber do this? I had two different cameras, both had the Sony HAD chips, and they were the subject of the tests described in the slides to follow. I used two different frame grabbers. There's a DFG USB 2 Pro, which is built by Imaging Sources. It's a relatively expensive device, $200 or so, depending on where you buy it, but it features uncompressed output and automatic gain control. The StarTech SVID2 USB 2 is a relatively low cost, $50 and change, that's in common use, produces MP4 compressed output, and does not have automatic gain control. I'll talk more about frame grabber automatic gain control toward the end of this presentation. Next slide, please. This is a schematic diagram of the major components that make up ArtStar. Across the top and down the left-hand side of this diagram are the mechanical parts, and there's lots of them. I stress this because the ArtStar Lite system that I'll describe later eliminates nearly all of them. The remainder of the diagram comprises the electronics portion of the system. The key piece is at the bottom of the diagram. That is where a microprocessor synchronized to the camera field frame times controls the illumination of two LEDs. And a central item is the IOTA VTI that has, I was able to grab a couple of signals from it, the GPS 1 PPS pulse and the field pulse that lets you know when the edge of the odd and even fields comes along. And that's critical to the illumination scheme that's used in ArtStar. Next, please. There are lots of bits and pieces. This is just some of the wooden parts. ArtStar doesn't need any of these. Next slide, please. So this is what ArtStar looks like, the mechanical parts assembled on my desk, waiting for the electronics to be attached. There's a yardstick in there so you can get some idea of the scale. And there's also a fiber optic cable there that's stuck in the end of that light tube and is used to produce an artificial star. Next slide, please. And this is what ArtStar looks like in operation. There's a digital oscilloscope that's peeking in from the left, and that was used during hardware development to confirm pulse timing. The next slide shows what the camera is seeing as it peers up the mailing tube. Next slide, please. So that's what the video camera sees. The star shines from the output end of a 50-micron fiber optic cable. The target marked bar is one segment from a 10-segment bar graph LED. The microprocessor is able to control the brightness of these targets on a field-by-field basis using the scheme that I show in the next slide. Next slide, please. The key idea in controlling target illumination in ArtStar and ArtStar Lite, which uses the same electronics, shown in this slide. The red pulse train at the bottom shows the field timing waveform extracted from the composite video by the IOTA VTI. The microprocessor controls when the LED that lights a target will turn on and off. To get half the number of photons delivered to the camera, we simply cut the time the LED is on in half. This is an inherently linear process, provided one can avoid heating effects in the LED. That's easy to do here, because typical currents delivered to the LED are just a few microamps, sometimes less. These cameras don't need much light, so the LEDs don't need much current. The next slide shows the response of a Watec 120N Plus to LED illumination that linearly increases from 0 to 100% using this scheme. For this measurement, I was using the DFG frame grabber. That's the more expensive one that features uncompressed video output. ArtStar can also modulate the current to the LEDs rather than the on time. Next slide, please. When you do that, you don't get this nice linear plot. The previous slide showed that ArtStar can provide field-by-field linear illumination when run in pulse width modulation mode. At this point, I switched to using a Watec 910 as the camera under test, and the first surprise appeared. Actually, there were two surprises. Next, please. Now this was a surprise. The kinks in the response curve were unexpected. In fact, so much so that I was concerned that the frame grabber might be responsible. So I switched to the SVID frame grabber, and the kinks almost, but not quite, disappear. The brown dotted lines show the light curve recording with the SVID frame grabber. Subsequent measurements of the amplitude of the composite video from the Watec 910 showed that it was larger than the expected standard 1-volt peak-to-peak. The SVID frame grabber does not have AGC to compensate for this. I'll show that in a later slide. So it was actually clipping the output. The DFG frame grabber has a very effective automatic gain control, and so records the full camera output. So now the question was, were the kinks particular to my camera, or was this response curve typical? So time to talk to the manufacturer. Next slide, please. A communication with the vendor, a nice little email exchange, resulted in a prompt and helpful response from an engineer who was involved with the 910, and he confirmed that the ArtStar measured response curve was consistent with their design intent, and that this is the plot that he provided for us. He added that if a completely linear response curve would be more useful for our application, they could provide the red response curve if we wanted it. We'd have to select that option at order time, and there'd be some fee involved in customizing the camera for us. I'm going to switch now briefly to a frame grabber comparison, frame grabber compression discussion. Next slide, please. I'm just going to read the slide and then comment a little bit. Most frame grabbers produce a compressed video. It's rather difficult to find one that doesn't produce an uncompressed video stream. The DFG frame grabber does output an uncompressed video. It's a Y800 format video. The SVID frame grabber produces an MP4 compressed video. So one of the important questions to be answered is whether this compression affects occultation timing. To answer this question, ArtStar was designed to be able to replay an actual occultation frame by frame. This is shown in the next slide. Next slide, please. This shows one experimental run. In the replay mode, ArtStar begins with maximum illumination. So that's the left-hand edge of the light curve, that part above 5,000. It then switches to zero illumination and plays a linear illumination ramp. This lets one know that the camera is actually operating in its linear mode, or not. Here it clearly was. After a brief pause, an actual occultation light curve is used to modulate the illumination frame by frame. When such curves are recorded with and without frame grabber compression, subsequent DNR estimations from IOTA can be used to determine whether the compression adversely affected the DNR times. Limited testing performed to date indicates that there is no statistical difference in DNR times extracted from MP4 videos versus uncompressed videos. Now here I'm only talking about frame grabber compression, not any tricks the camera itself might be doing. Which brings me to the next section of this presentation and an area that caused me a lot of struggles: microlens effects and what is known in the literature as subpixel response. Next slide, please. Sony has shown diagrams such as this one. This is from a white paper that Sony published about their HAD and super HAD devices. The point to be made here is that the unit cell that we think of as a pixel is a complicated structure. Next slide. This diagram foretells the phenomena known in the literature as subpixel response. By subpixel response is meant the variation in electrical response to an incoming photon based on precisely where that photon hits the pixel. Some areas are completely unresponsive. Others are partially responsive in comparison to what it would be if the photon hit squarely in the center of the photosensitive region. Next slide, please. So this is an image recorded of a best focused star through the light tube. This was shot at f2.8, and it was the best focus that I could achieve. Calculation of the star size using ArtStar optics show that the 50 micron diameter star, that's the end of the fiber optic fiber, projects onto the CCD array as a 4 micron spot. Well, the unit pixel in both the Watt 120N Plus and the Watt 910 is 8.4 by 9.8 microns. Therefore, it should be possible to light a single pixel, but it isn't, as this slide shows. This is more likely a microlens effect rather than due to charge diffusion, which does affect backlit CCD arrays. Under these conditions, with the 4 micron spot, you'd think that only a single pixel should be lit. We should have gotten something that looked more like a hot pixel. Instead, neighboring pixels are quite well lit. I'm guessing that this is a scattering effect caused by the microlens structure, but I could find no way to test that hypothesis. So at the moment, my conjecture is an opinion. To investigate microlens structure phenomena, ArtStar is equipped with positioning screws that have a fine enough pitch that the spot can be positioned with sub-pixel precision. Those positioning screws are shown in the next slide. Next, there we go. So I got some arrows that show you 2 of the positioning screws. There's a third hidden behind the camera lens. With these positioning screws, you can move the star image slowly across the pixel array. It's quite a fine pitch screw that I'm using there. When one does that, you get a light curve like the one shown on the next slide. So here's how I did this. The recording was started with an unsaturated star image. The illumination was very much in the linear range. At point A on the light curve, I began slowly twisting one of the positioning screws. And you can see up to point B, it gets rather, well, there's a lot going on. At point B, I reversed twisting of the position screw until I reached approximately the original starting position, which brought us back to point C. So this result caused me to conclude that my artificial star was, well, just too artificial. In field observations through a telescope, the point spread function, PSF, of a star image, whether caused by the telescope optics or more commonly by seeing, it extends over multiple pixels, and that mitigates the effect of this subpixel response. So for me, a natural question was, what should the FWHM, the full width half maximum, or width of a point spread function be to minimize the effects of this subpixel response characteristic? I did the following little study to get some feeling for this effect. Next slide, please. So I made a guess at the subpixel response based on the electron microscope picture shown in an earlier slide. So where it's red, that's where you have maximal response to an incoming photon, and where it's blue, that's where it has much less or none. So next slide, please. This is just such a pretty picture. I just had to show it. This is my hypothetical pixel replicated in a 21 by 21 array. Actually, it wasn't just a pretty picture. The plan was to project a point spread function onto this response pattern to see what the effect of the response variations across a pixel would have on the cumulative observed response. Next slide, please. Here is a plot of one of the spread functions that I used. This one was approximately 4 pixels in width. Next slide, please. This is what happens when you convolve that point spread function with the pixel array responsivity. You get these little spiky nodules. The next step in my simulation was to position the center of the PSF over a unit pixel divided into 100 regions. At each sub-pixel position, I did a numerical integration of the entire point spread function to simulate the response to this width point spread function at this particular position. From these 100 values, the minimum, maximum, and average of the integrated response was recorded. This process was repeated over a range of widths, FWHM sizes, and plotted as shown in the next slide. This is a bit of an eye chart even for me. But this slide suggests that subpixel response effects do not affect camera output whenever point spread functions are 2 pixels or larger in width. This is commonly the case with telescope, camera, focal reducer, and seeing conditions encountered in occultation observations. I should point out that this simulation does not model the effects of the microlens structure. I personally believe that the microlens structure produces a scattering effect that is not well captured by the simple model used in the simulation. Even so, this plot went a long way toward explaining the light curve variability shown in the earlier slide, where the positioning screw was used to traverse the star image across the pixel array. I concluded that something had to be done about the ArtStar star. It was just too small and well focused. Next slide, please. I think just reading this slide really tells the story. It's pretty clear I needed to have a better star image. So I had some precision holes laser drilled in some stainless steel aperture discs that I could put at the front surface of the camera lens, replacing the built-in aperture stop of the camera lens. I had 5 diameters drilled. And I found that the 2000 micron aperture produced a PSF of about 6 pixels wide, and this was used for most of the measurements involving the star image. So I got a reasonable simulation optically, but I have to question how accurately it reflects a real telescope PSF that really results from seeing conditions rather than optics. I mean, what happens is you get an effective point spread function, not because your telescope optics are doing that, but because your star image is dancing and it's wiggling on the screen, and that kind of integrates out to a point spread function that looks very much like the Gaussians that we've seen in the previous slide. The next slide, please. Unfortunately, this slide is mislabeled. It shows what it calls a 2000 micron aperture PSF. Actually, this was done with the 500 micron aperture, because this resulted in a width, a PSF width, I think it's pretty clear from the upper left, that was about 13 pixels. But if I put a 2000 micron aperture in place, I get a star image with a PSF in the 6 pixel width range. And that's pretty well confirmed by looking at it visually. And when I run it through LiMovie or Tangra, the Tangra and LiMovie both agree I've got, on the range of 6 pixel FWHM. So this looks a lot more like what's obtained in field observations. Just as a reminder, the next slide shows what the star image was before the installation of the pinhole aperture system, and you can compare that with the upper left. Next slide, please. I'm going to move on to a description of ArtStar Lite. There is more information available about ArtStar. There was a fairly detailed report that was published on Yahoo IO occultations group site. Here's some links that you can get to if you have more interest. Next slide, please. So, ArtStar Lite. ArtStar Lite simplifies the mechanics, but retains and reuses the electronics of ArtStar. It's able to make all of the measurements that ArtStar does, except for those, of course, that depend on the specifics of a starlight target, because ArtStar Lite gets rid of it. Next slide, please. So here's the mechanics of ArtStar. It's just a few pretty easily obtainable parts that take the place of that big light tube we saw in the earlier slide. There's a little plywood plate and an LED. You drill a hole in that plywood plate and you press the LED through it. And then you take a PVC plumbing fitting and a C-mount 1 1/4 eyepiece adapter. And I've wrapped tape around it so that it's a nice press fit into that PVC plumbing fitting. And inside that C-mount eyepiece adapter, I've built a light diffuser. Next slide, please. So this is how the light diffuser was put together. It's really just 2 discs of paper cut from regular, 24-pound copy paper. And there's 2 of them in series. And the left-hand side shows looking from the camera side. If you turn that upside down, now you're looking from the LED side, and there's another paper disc. And they're spaced by this little neoprene foam, which keeps them separated, keeps them in place, and it actually acts as a light seal when you screw this whole thing onto your camera. Next slide, please. So this is what the whole thing looks like attached to a Wattec 910 camera. I'd like to mention in passing that ArtStar light could even be mounted so that it shines through the lens cover of a telescope. So you don't actually have to take the camera off your scope. You would have to, I guess, drill a hole or something else on the lens cover of your telescope, but this would result in a very fuzzy blob being imaged by the telescope lens onto the CCD array, but the same measurements of camera response would be possible, except now they will be in situ measurements. This could be important if there are other optical elements, maybe filters, that need to be tested simultaneously and don't otherwise fit the mechanical model of either ArtStar or ArtStar Lite. Next slide, please. So this is what images through ArtStar Lite look like. They're just flats. And the flats have an intensity that's under microprocessor control on a field-by-field basis, exactly like ArtStar. So another surprise. Next slide. Kind of a complicated experiment. I started with the LEDs off, and then I turned the image on to about half intensity, and then I turned it off and started a linear intensity ramp, and all this was actually automated in my testing software. And by having this particular pattern, I was able to use automated software to find the starting point and end point of the linear ramp. Okay. So the surprise here is that although the response curve is linear, that linear curve does not extrapolate through zero. Now, one would expect that photometry is going to be affected by that fact. In effect, there's a small amount of light that reaches the camera but does not produce a corresponding output. It's a thresholded out of existence. And I'm going to argue that this characteristics of the Watt 910 response curve explains something that was previously reported by Hristo Pavlov, but was mysterious at the time. Next slide, please. The slide is shown with the approval of Hristo. He ran a very, very interesting experiment where he imaged a star field through a red filter and very carefully set things up so that none of the stars of interest were saturated. He used aperture photometry. Along the vertical axis, he's showing the star magnitudes that he pulled from a catalog. And on the horizontal axis were the instrumental magnitudes that he measured. Now the expectation would have been the slope of that curve would have been 1, but that's not what he got. He got something less than 1, 0.89, 0.90 roughly. So the mystery was, why doesn't the straight line above have a slope of 1.0? What the straight line in this slide demonstrates is that if the star catalog shows a mag drop of 1.00 between two stars, the instrumental mag drop records a 1.115 mag drop between those same two stars. This effect can be simulated using ArtStar with the 2000 micron aperture as shown in the following slide. So the upper light curve is an automated test where I start at 0 and then provide maximum illumination, and every 1,000 frames I reduce the illumination by a factor of 0.7943, what amounts to a 0.25 mag drop. I should point out that Hristo's plot covers 2 magnitude change, while this test covers a slightly larger 2.5 magnitude drop. The text box below and to the right shows the instrumental mag drops calculated from the light curve. The plot to the left, and this is really the money plot, shows graphically the measured mag drops compared with the expected value shown in the red line. The red line says that all the mag drops should have been at 0.25, but you can see starting from the right-hand side moving to the left as you go to dimmer and dimmer stars, that the effective mag drop keeps increasing. Now that's the same phenomenon that was depicted in Hristo's plot. When the magnitude calculated mag drop is 1.00, the measured mag drop, instrumental mag drop, is always greater. I'm claiming this is due to two things. First, the point spread function having wing pixels with intensities close to 0, and the Watt 910 response curve not going through 0. So the wing pixels that are close to 0 are going to be more affected by that little light curve that didn't really extrapolate through 0 than the stronger pixels in the center. To demonstrate that the shape actually matters, I used ArtStar Light to repeat the test. So that gave me, lots of pixels to pick from that had uniform illumination. So I repeated the test, measuring the response from a 16 pixel block. The following slide shows the result of this test. I guess the first thing that's obvious is that it's not quite as noisy, and that's because I'm looking at lots of pixels and they're getting averaged together. And the money plot, again, is the lower left-hand plot. And except for a couple of points in the last couple of mag drops, the actual mag drop versus the predicted mag drop all hit 0.5 as expected. So this really shows that mag drops in the range of 0 to about 1.75 are very accurate. It's not until mag drops exceed 1.75 that the effect of the response curve not going to 0 begins to show itself. After a brief discussion of frame grabber automatic gain control, I'm going to wrap up. Next slide, please. So automatic gain control acts differently in a frame grabber than it does in a video camera. In the camera, the automatic gain control acts on the image. In a frame grabber, it acts on the total composite video signals. Now, frame grabbers may or may not have automatic gain control. When this is present, the automatic gain control compensates for non-standard amplitude composite video signals. Such out-of-spec signals can arise from the camera electronics and/or cable impedance mismatches. To understand how automatic gain control works when present, we need to look at the next diagram. So this is what a composite video looks like in the diagrammatic form. The left-hand part of the waveform, which starts at 0 and drops to minus 40 in units of what they call IRE, which are really arbitrary units. But the important point is that that area, that 0 to minus 40, has a standardized voltage. It's supposed to be a certain voltage. So when a frame grabber implements automatic gain control, this is the part of the composite video that it examines in order to select the proper gain. The gain needed to adjust this part of the signal back to the correct voltage swing is applied to the total signal. The video data is on the right-hand portion of the waveform. For our cameras, the video data appears in the region that's labeled black level to white level. So you can see black level, there's a little arrow that comes in from the right-hand side, and white level is more clearly obvious up there at the top at 100. Now this diagram does show signals above the white level, but that's only present in a color TV composite video. I just picked this one because it seemed pretty clear, even though it wasn't completely relevant for us. So the next slide shows the response of two frame grabbers to a composite video signal that has been deliberately modified in peak-to-peak amplitude by passing it through an attenuator. So this is what I did. You know, I got an attenuator that's got a knob on it, and you just can twist the knob, and it can control the attenuation of the composite video from an attenuation factor of 0.9 down to 0.5. It can be the DFG frame grabber is at the upper one, and you can see it has a very effective automatic gain control, because every so often I was twisting the knob and I went through 4 steps down and then I moved 4 steps back, and others than some tiny little glitches. As far as the DFG frame grabber was concerned, it just adapted itself to the peak-to-peak amplitude of the incoming composite video. Now, the StarTech frame grabber doesn't have AGC, and that's shown in the bottom. And so here you can see whenever I changed the composite video amplitude, I get a reduced light curve output from the camera. So question, does this really matter to us? Well, it was the source of the clipping that we saw in one of the very early slides, and effectively reduced the dynamic range of the camera, and it hid a camera response characteristic of some importance. But if the composite video signal had not been out of spec, it was too big, this wouldn't have happened. I still use the StarTech grabber, but I make sure that the video amplitude is at the correct level. Next slide, please. So in summation, I just provided a brief description of the ArtStar testing system and introduced ArtStar Lite, which is a mechanically simplified version of ArtStar, and just highlighted several surprises that I ran into in building and subsequent tests. Most significant among them really is the unexpected kinks in the 910 response curve, and then the effects of a too small star image. And then the otherwise linear camera response that doesn't pass through zeros seemed to provide a reasonable explanation of Hristo-Pavlov's mag drop plot. The good news is that none of those surprises affected timing, only photometry. That concludes this presentation. Are there any questions?
What I've noticed about my 910 HX camera is that it has a peculiar black level when you look at the video. Instead of showing a noise background, it often is perfectly black. And I take that as basically the same thing as you found, that it has a non-zero, the dose, what I call dose response, what do you call it, stimulus response curve doesn't cross the zero line. You have to get a certain threshold before you get any light response. And in that respect, it's different from the other Wattec cameras that I use, because they seem to have a noisy background for all my observations. And secondly, what occurred to me when you were talking about the point spread function being too small, and you didn't understand why it would be more than 1 pixel, why it didn't look like a hot pixel, and you were concerned that there might be an effect of the lens, the micro lenses, causing the point spread function to have the width that it had. It occurred to me that it may just be diffraction at the surface of the chip, of your video chip. And a simple way to test that is, I mean, in fact, the size of the pixels are such that they would be prone to a great deal of diffraction, and diffraction is the cause of irradiation in video chips. And so what I would be interested in is whether you would find that the diffraction is greater in red than in blue. You were using a red laser, and you never tested it in other colors, but you would ordinarily expect the diffraction to be greater in blue, in red. So that would just be a simple way to test that. And I know you're already in this over your head. As you've indicated, it has a life of its own. but I just wanted to share those thoughts.
Go ahead and thank Bob and proceed.
Okay, well, Bob, that was a fantastic talk on a lot of research and some basic stuff that we need to know about our video cameras, and I appreciate all that you've done about that, and thank you for sharing it with us.